Hi there, my name is Stephanie Labason. I'm sorry I couldn't join you this week in Brazil, but this afternoon I wanted to give my presentation on power and performance trade-offs for visualization algorithms. I'd also like to thank my co-authors, Matthew Larson and Barry Roundtree of Lawrence Livermore, and Hank Childs of the University of Oregon. Our study was motivated by the power limitations at exascale. One solution, in addition to general hardware improvements, is hardware over-provisioning, or over-provisioning for short. With this solution, we have a system that contains more nodes, but we enforce power limits across the nodes, thus degrading the performance of the running applications. The underlying premise of this study is that visualization algorithms will behave differently than HPC applications under power limits, and this is because visualization workloads are data intensive. In this study, we considered a representative set of visualization algorithms and investigated the trade-offs between slowdown and power usage. The outcome of our study is a better understanding of the execution characteristics for visualization and analysis routines under power limits, and this is particularly important because we can then exploit those characteristics for overall better performance. So here's the outline for this talk. I'm first going to start with motivation of the two topics that are at the intersection of this research, and then talk about those two topics in context together. So here I'm showing the system power usage for the BlueGene-Q supercomputer at Lawrence Livermore, known as Vulkan, over the course of several years, dating back to February of this year when the system was retired from use. This system is provisioned for 2.4 megawatts of power, and this number is derived assuming every node in the system will consume peak power at the same time. One of the first steps we do when we receive a new machine is run our highly optimized benchmark known as LinPack to stress test the system, and we see that this application comes very, very close to the 2.4 megawatts that the system was provisioned for. And once we hand control over to our other simulation codes, they are only able to achieve roughly 1.5 megawatts of power, or roughly 60% of the provisioned power. Now, this isn't a pattern that we see just on BlueGene-Q systems. We've also experienced this similar behavior on an Intel Broadwell system, also at Lawrence Livermore, known as Quartz, and we see the same behavior where our other codes are only able to consume roughly 60% of the provisioned power for the given system. So our current assumption, or our current strategy, where we assume that all the nodes in the system will consume peak power at the same time, is suboptimal because it not only limits the size of the system that we procure, thus reducing system throughput. Additionally, there's power capacity left on the table. In the course of the Vulkan machine, we're leaving roughly 1 megawatt of power unused, and we could have used this power to accomplish more science. System power usage is rising to unsustainable levels, and as a result, power is becoming an increasingly scarce resource, not only due to the expensive costs. The typical assumption is that 1 megawatt of power sustained for a year will cost a supercomputing facility $1 million, or roughly 4 million Brazilian reais. Additionally, there are limitations being enforced by supercomputing facilities. The Department of Energy has set a target for reaching an exaflop of computing at 20 to 40 megawatts of system power usage. And so it will become very important for us to maximize the limited power resource in order to reach our computational goals. A key premise here is that in order to meet our power consumption goals at exascale, we need to innovate power efficient techniques, not just in hardware with accelerators and many core technologies, but also in software. As previously mentioned, one strategy to improve power utilization is hardware over-provisioning, or over-provisioning for short. Our current traditional approach when procuring systems is to assume that all nodes can run at peak power simultaneously, assuming some provisioned amount of power for the given system. But as we've seen on previous slides, this is a suboptimal strategy that leads to limited throughput and power capacity being left on the table. Alternatively, we can have an over-provisioned system where we increase the compute capacity by adding more nodes to the system, but all the nodes will not be able to run at peak power simultaneously under the provisioned power bound. And so what we do is we limit the power usage per node. So for example, with an over-provisioned system, it may contain 2 times the number of nodes, thus increasing the compute capacity. But now we're only able to run the nodes at half the amount of power. But this is more beneficial to the common types of applications that we run. So for this over-provisioning strategy to be effective, all the aspects of the HPC ecosystem, including our visualization and analysis routines, must be reconsidered with power in mind. Limiting the processor power usage can be done by enforcing a hard power limit. And the outcome here is that your application takes longer to run, but it uses less power. This is because there's a nonlinear relationship between power and the CPU frequency. So as you lower the power limit, you're effectively lowering or limiting the CPU frequency, but your subcomponents still consume power at the same rate. And depending on the application's instruction mix, its response to different power limits will vary. So here on the right of the slide, I'm showing the relative performance for several different benchmarks at different power limits. So on the x-axis, we have processor power limits ranging from 50 watts up to 115 watts. And on the y-axis, I'm showing the relative performance to the application's best performance, which occurs at 115 watts, which has the highest CPU frequencies. And we see that our more compute-bound benchmarks tend to slow down proportional to the lower power limits. And this is because those applications' instructions are highly dependent on the clock frequency, which is being limited severely as we lower the power limit. On the other hand, applications that are more memory-bound do not slow down proportional to the power limit. And this is because those applications are not dependent on the clock frequency of the processor. And so they are not impacted as we slow down as we lower the power limit of the processor. The power limitations at exascale will impact all of the different types of applications that we run on our systems, ranging from scientific simulations to visualization and analysis routines. In order to reach our computational demands, we need to use the power wisely, and this may require us to have some central manager that's coordinating the power allocations throughout the system to ensure that we're not exceeding our provisioned power bound. And so given some power constraint, the central manager would then adjust to the application configuration accordingly to be sure that it fits within the power bounds. The visualization community is moving towards a workflow where the visualization and analysis will run concurrently with the simulation. This is known as in situ. And this new workflow will challenge us to understand not just how the simulation behaves under a power limit, but also how the visualization component behaves under a power limit. And this visualization component is the piece that we focus on for this study. So now we'll look at why, or the importance of visualization, which is a use case for this study. There are 3 main reasons why visualization is important in a power-limited environment. First, visualization is important for scientific insight. Second, visualization will be running concurrently with the simulation and sharing compute resources. And the visualization component is able to consume significant resources on the HPC system. And third, with over-provisioning, visualization workloads will respond differently than the simulation workloads. And so I'm going to cover number 1 and number 2 in the next couple slides, and I'll cover number 3 in the next section of the motivation. Visualization is important for understanding scientific simulation data. It enables us to transform abstract simulation data into a comprehensible image. We typically use visualization for 3 different use cases. The first is to communicate through movies and pictures our results with a larger community. The second is to validate that our simulation is behaving as expected and hasn't diverged. And the third reason we use visualization is to explore some new phenomena. Traditionally, visualization is accomplished with post hoc processing, where the visualization occurs after the simulation has finished executing. However, this approach will not be feasible at exascale, since the rate at which our applications are able to compute and generate data is rapidly outpacing our ability to save the data to disk. And so to bypass the I/O gap, the visualization community is moving towards in situ, where the analysis and visualization will occur while the simulation is running. So if we want to optimize the power usage for better performance, we need to be aware of not just the simulation, but also the visualization, which can be 10 to 20% of the total runtime. Now we'll talk about over-provisioning and visualization in context together. So visualization in an over-provisioned environment merits special attention. Visualization workloads are different than the simulation, and so we need visualization-centric techniques to be able to thrive in this power-constrained environment. Visualization workloads are different than that of the simulation, which typically have one key loop that can be optimized for better performance. The visualization community, on the other hand, has hundreds of different visualization operations, and the execution behaviors of these operations are highly variable from one operation to the next. Further complicating this space are the different configurations that you can select for each of these operations, depending on what you as the user are most interested in seeing. In visualization, we often pipeline many of these operations together to create a visualization pipeline, where the operation of, or the output data of one operation will be dependent on the input data that was received from the previous operation. So if we want to optimize the performance of the overall visualization pipeline, one strategy would be to optimize the performance of each operation in that pipeline individually. But since there are so many different combinations of operations and configurations, it's not a practical approach. So we identified a set of 8 visualization operations that we thought covered the wide span of different execution behaviors that exists across all the different visualization operations. And so our study is foundational for understanding the execution behaviors for this set of visualization operations under different power limits. So this brings us to our research questions. We first wanted to understand how visualization workloads perform under power limits. And secondly, we wanted to understand if an application must run at a lower power limit, how much slowdown will it see? Now we'll go over the experimental overview. We looked at 3 different study factors. The first factor we varied was the processor level power limit. For our experiments, we used a single node of Livermore's Topaz system, which is an Intel Broadwell system. Each node contains 36 cores running at 2.1 gigahertz. Setting power limits is generally a privileged operation, but we were able to leverage Livermore's MSR Safe kernel driver to set power limits on the system from user space. The power limits are enforced with Intel's RAPL technology. This is a 64-bit register where you set the power limit over a particular time window, and the underlying firmware will change the underlying CPU frequencies to guarantee the given or the specified power limit. So on this system, the acceptable power limits for the processor range between 120 watts down to 40 watts. We also looked at different visualization algorithms. So again, we selected a representative set of visualization algorithms to explore under different power limits for this study. And these are renderings of each of the different algorithms. We also looked at different data set sizes. So for this application, or for this study, we used the Cloverleaf 3D application, which is a hydrodynamics mini application. We varied the data set size per node from 32 cubed up to 256 cubed, which is limited by the given or the particular memory size per node. And so the number of cells per node ranged from 32,000 to 16 million. Our study was conducted in 3 different phases. In phase 1, we varied the power limit for a single visualization algorithm and particular data set size. And the subsequent phases varied 1 factor at a time to investigate the effects. So in phase 2, we varied the visualization algorithm, and in phase 3, we'll vary the data set size. Now we'll look at our results. So in phase 1, we varied the processor level power limit. Here on the table on the right, I'm showing 6 different columns. The first column is P, which stands for the power limit. This ranged from 120 watts default down to 40 watts. And we calculate the P ratio by dividing the default power limit of 120 watts over all of the reduced power limits. So that would be 110 watts down to 40 watts. For our column T, this is the raw performance of the given algorithm at that particular power limit. And we derive the T ratio by taking the time at the reduced power limit, which is where the time should increase, over the time at the default performance, which is the lowest power limit, or the lowest, fastest performance time. We also looked at CPU frequency, which is listed in column F, and we compute the frequency ratio by dividing the default frequency at 120 watts over all of the reduced clock frequencies at the reduced power limits. So at the default power limit of 120 watts, we see that our contour algorithm, which is the one we used in this particular phase, took 33.5 seconds to run, and the clock frequency was operating at 2.5 gigahertz. Now as we start to slow down the power limit, if the contour algorithm was significantly compute bound, we would see that the T ratio would be comparable to the P ratio. But in this case, the contour algorithm only slows down by a factor of 1.2, while we slow down the processor power limit by a factor of 3. And we also see that the frequency slows down by the 1.2 factor as well. So by reducing the power limit by a factor of 3, we're able to achieve power savings without degrading performance. Here in phase 2, we wanted to execute all the visualization algorithms under different power limits. And the goal here was to investigate the data intensity of different visualization algorithms. So in phase 2, we identified that our algorithms fell into 2 different categories: power opportunity and power sensitive. Our power opportunity algorithms, which we show here on the left side, have a performance that remains constant until the most severe power cap of 40 watts. So the algorithms that fell into this category tend to be our more cell-centered data sets, where we need to walk across each individual cell and do some operation. On the other hand, our power sensitive category these algorithms saw the performance degrade relative to the power cap. So these tended to be our more compute-bound workloads. So particle advection and volume rendering fell into this category. We also initially thought that ray tracing would fall into this category as well. But upon further investigation, we identified that ray tracing is really a pipeline of 3 different visualization operations. The first is finding the external faces. The second is building a spatial acceleration structure. And the third is tracing rays. Tracing rays would be the more compute-bound operation in this pipeline, but it's being dominated by the time it takes to find external faces, which is more data intensive and why this algorithm fell into the power opportunity class. So now we wanted to look at 2 different algorithms in more detail, one from each class. So for power opportunity, we're going to look at threshold. For threshold, we iterate over each cell in the data set. And for each cell, we remove or we compare it to the specified range. If the cell does contain values in that range, we keep it and put it in the output data set. And if it does not, then we remove the cell. And so the simple computation of doing this comparison is being dominated by loads and stores of each cell. And this is why this is a more data-intensive algorithm. For particle advection, which is a power-sensitive category or power-sensitive algorithm, we place a massless particle at some seed location, and then we displace that particle according to the vector field. And so the result becomes an integral curve, which corresponds to the trajectory or the path that that particle had traveled. And there are several different implementations like Euler's and RK4. So we wanted to look at some performance metrics for each of these algorithms to better understand their behaviors under different power limits. So one of those metrics that we looked at was instructions per cycle, or IPC. And this is a metric that indicates how compute-bound an algorithm can be. On the other hand, we also looked at last level cache miss rate. And this is more indicative of how memory-bound a particular algorithm is. So first we're going to look at the metrics for the threshold algorithm, which is a power opportunity algorithm. So for this algorithm, we saw that it had a very low instructions per cycle, which is indicative that it's more memory-bound. And upon looking at the miss rate in the last level cache, we see that its miss rate is very high in the last level cache. And this makes sense because it's not able to execute as many instructions per cycle because it's waiting on memory requests to be satisfied and brought into the caching infrastructure. On the other hand, if we look at the metrics for particle advection, which is a more compute-bound workload, we see that its instructions per cycle is very high relative to the threshold instructions per cycle. And we also see that its instructions per cycle starts to tail off with a reduction in the power cap. And this is because this algorithm is very dependent on the processor. And so as we start to lower the processor power limit, the speed of the processor itself starts to also slow down, which really impacts the rate at which instructions can be executed. The reason that particle advection is able to execute so many instructions in a given cycle is because it has a very low miss rate in the last level cache. And so this means that it's not needing to spend time grabbing data from the memory subsystem. It already has the data it needs and can continue executing. Now in phase 3, we wanted to execute all visualization algorithms with different dataset sizes. The goal in this phase was to investigate the impacts of dataset size on power and performance trade-offs. When we varied the dataset size, we found that our algorithms fell into 3 different categories. So on the x-axis in these figures, we have processor level power cap ranging from 40 watts to 120 watts. And on the y-axis, we're showing the instructions per cycle. So our first category of algorithms saw an increase in instructions per cycle as the data set size increased from 32 cubed to 256 cubed. So for these algorithms, they became more compute intensive as their instructions per cycle increased, as the data set size increased. The algorithms that fell into this category tended to be our cell-centered algorithms like threshold and contour, where we are walking across all the cells in the data set size and performing some computation. As the data set size increases, we start to amortize the cost to load and store each data set, and the number of computations or the level of computation starts to dominate the workload. Our next category of algorithms were those that saw a decrease in instructions per cycle as the data set size increased. Volume rendering was one of the algorithms that fell into this category, where we saw the algorithm becoming more data intensive as the data set size increased. So as the data set size increased, we saw a drop in the instructions per cycle. Volume rendering in particular, as the data set size gets larger, starts to thrash the caching infrastructure more, making it more data intensive and less able to perform or execute as many instructions per cycle. Our last category of algorithms saw no change in the instructions per cycle as the data set size increased. And for this category, particle advection fell into this class. And we believe that because we kept the number of particles, the step length, and the number of steps constant, regardless of the data set size, that we were seeing the constant instructions per cycle. If particles were being displaced outside the bounding box, which may change with the changing data set size, they terminate and there's no further instructions to execute. Now we'll dive into our conclusion or takeaways and future work. So our takeaways from the study inform how visualization workloads can adapt to the imposed power limits at exascale. In phase 1, we showed that the contour implementation is sufficiently data intensive to avoid a significant slowdown when the power limit is reduced. In phase 2, when we varied the visualization algorithm, we saw that most of the algorithms consumed low amounts of power, and this provides opportunities for savings in power because they're data intensive. And in our last phase, where we varied the data set size, we saw that the trade-offs became more favorable with a smaller data set size per node. So our future work, we want to integrate all of these findings into a power-aware runtime system such that we can make more informed decisions about how to allocate power in an in-situ workflow. This brings me to the end of my talk today. Thank you to everyone who attended this afternoon, and special thanks to the paper chairs and the organizers for being so accommodating over the last couple days and letting us present this paper remotely due to a last-minute change in travel plans. If you need to contact me or have any questions, my email is there at the bottom of the slide. You can reach me at brink2@llnl.gov. I hope everyone has a great week at IPDPS and has a wonderful time in Brazil.